So for our final video dealing with rate laws in the order of a reaction, I want us to look at how we could calculate rate order if we don't hold both reactants constant at some point in the reaction. Let's look at this data right here. Now we have to have one set of experiments where we do hold these constants. So we would have to have something in this instance where we have A held constant in both experiments 1 and 2. But we're going to pretend that B was not held constant. And so rather than looking at experiments 2 and 3 like we did for inspection, we're going to pretend that those were not constant, and we're going to take two that are not the same. We're going to look at reactions 1 and 3. And we're going to set up a ratio. And the ratio is going to be the rate law of one of the experiments over the rate law of another experiment. And we're going to be able to use that to calculate our order. Now, when you do this, you always want to have the one with the highest rate on top. It just makes the math easier. You don't have to do it that way, but it really does make the math easier. So the first one we're going to do is rate 1 versus rate 2, and which one would we need on top? We would need the one with the biggest rate. So we're going to go to the next page, or at the point where it says, down at the bottom of this page, where it says to do the calculation, and we're going to set it up so that rate 2 is on top and rate 1 is on bottom, and that's how we're going to set up our rate law or our proportion. So let's go down here to our calculations section. And once again, we're going to do rate 2 over rate 1. And we're going to set up our general rate expression for each of these. So we're going to have K A to the M, B to the N on top, and K A to the M, B to the N on bottom. And to distinguish between the two, we're going to put 2's after all of these and 1's after these. So let's fill all the values in. If you look back up at the table, now I'm not going to be switching back and forth to the table, so you'll have to have it handy. But the initial rate for 2 was 6.0 times 10 to the negative 3 molarities per second. And our initial rate for reaction 1 is 2.0 times 10 to the negative third molarities per second. We don't know at this point K for either one of them. This is before we ever are able to find K. Now the concentration of A for reaction 2 or experiment 2 is 0.1 molar, and that's going to be raised to the M. And for the value for B is going to be 0.3 molar, and that's going to be raised to the N. For reaction 1, A was still 0.10 molar, and so was B. Okay, so that's going to be our equation that we're going to solve. And let's look at what happens there. Now, one thing we know about K is that if we're at the same temperature, then the K values are constant for these reactions. So these have to be at the same temperature. We can't determine rate order, so these K's will cancel. Look at what else will cancel. We're canceling this term and this term. So what it actually leaves for us to work with for our equation are these two terms. Now, keep in mind, I'm going to write this off to the side over here. Keep in mind that if you have 0.3 molar over 0.10 molar, and both of those are raised to the same power, the laws of exponents say that that's the same thing as saying 0.30 molar over 0.10 molar quantity raised to that power. So if that's true, all we need to do is to divide those two, 0.3 divided by 0.1, and we see that this becomes 3 to the n. And that's what we're going to get for this right-hand term over here is 3 to the n. And if we divide 6.0 divided by 2.0, both of them times 10 to the negative third, we get 3 for that as well. Well, hopefully you can see that any number raised to the first power is going to be itself, so it looks like n is equal to 1 here. So that's how we would determine that this is first order with respect to b. And that's how you would be able to say that now. So now that we know what the value for n is, we can take an equation that has nothing that cancels, and we're going to be able to find the other exponent. We're going to be able to find m. Now we said for m, we were going to show the relationship between reactions 1 and 3 over here. And notice that the biggest value between 1 and 3 is our 5.4 times 10 to the negative second. So that's what we're going to put on first, is on top is reaction 3. So let's go down here, and we're going to set up just like we did before. We're going to set up a proportion between rate 3 and rate 1. Rate 3 was 5, well, I'm getting ahead of myself. First of all, let's set up our general rate expression, and this is going to be K3 times A to the M times B. Now look at what we can do now. We can put a 1 here. So that's going to be important. On bottom, we're going to have everything just the same. We're just going to put little subscript 1s on them to denote that we're dealing with reaction 1. I'm sorry, it'd be better if I put those as M's. It would make more sense. So B again is going to be raised to the first power here. So I'm going to get rid of this part really quick so that we don't run into ourselves here. And let's plug in the values for these reactions. Rate 3 was 5.4 times 10 to the negative second, molarities per second. Rate 1 was 2.0 times 10 to the negative third molarities per second. And K3 over K1 our concentration for A for the experiment 3 is 0.30 molar. That's going to be raised to the M. And for B on the third reaction, it's also 0.30 this time, molar, raised to the first. For our first reaction, both of them are 0.1 molar. Oops, I just said that they were both 0.1 and I wrote it down wrong anyway. 0.1 molar, again raised to the first. So let's solve for this. Right now, the only thing that we can cancel are our K's. Okay. If we look at this next part, we see that 5.4 times 10 to the negative second divided by 2.0 times 10 to the negative third. Put that in your calculator, and you'll see that that comes out to be 27. Remember, we can take this term right here, and we can go ahead and divide 0.3 by 0.1, which is 3. And that whole quantity can be raised to the M now. And that is going to be multiplied by this quantity. So we've got 0.3 divided by 0.1 again, so we've got 3 again. Raised to the first, so anything raised to the first is itself, so it's just 3. Solving for 3m, 3 to the m, we see that 3 to the m is equal to 27. We're going to divide both sides by 3. 27 divided by 3, which is 9. And if this statement is true, in order for 3 to the m to be equal to 9, m has to be 2. So that's how we get an order when we don't have anything constant in our second reactant. So now we could say that the rate with respect to B is 1, and from this mathematical calculation we can say the rate with respect to A is 2. And we could go ahead, just like we did with the other, and now write our rate law, which is that rate is equal to K A squared B. So that's how we do it by calculation. Now we can do one more example using the other problem that we have on this worksheet, or on the set of notes, which is this one. We had a general rate law for this one of rate is equal to K pressure of NO to the M pressure of H2 to the N. So what we're going to do on this one is to, first of all, look at reactions 1 and 3. Remember, we have to make sure that one of our reactants is held constant for a couple of different experiments. But then we're going to pretend that this 0.4 situation here did not happen. So on the second one, we are going to look at the difference between these two reactions. So we can pretend that we don't have a constant value for our second reactant. So first one, we're going to take the difference between reactions 1 and 3. And remember, you always want to put the one that has the biggest rate on top. Which one has the biggest rate? Between experiments 1 and 2, experiment 1 does. So let's go down here for calculation. I believe it's on, might be in the next page. Yes, it's on the next page. And let's look at what we would need to put. So we're going to put rate 1 over rate 3. And it's going to be K, and it's not something different. Remember, we can't write this in terms of brackets. It's a gaseous reaction. To the M, to the N. And all of those are for reaction 1. And on the bottom, we're going to have K3, and exactly the same for the rest of it. We're just dealing with reaction 3 for this. Okay, so there's our setup for our ratio. Rate 1 is 0.020 atmospheres per minute. Rate 3 is 0.010 atmospheres per minute. We've got K1 over K3. Our pressure of NO for rate 1 was 0.15 atmospheres per minute. And the same thing for rate 3, experiment 3. Kind of running out of room here, but hopefully I can get this to fit on here. For experiment 1, it was 0.4. I'm just going to write 0.4 atmospheres per minute, squeeze it in to the N, and 0.4 atmospheres per minute, clearly atmospheres per minute, raised to the N. I'm sorry, that's 0.2 on the bottom. So I'm going to try it again here. 0.2 atmospheres per minute raised to the N. Okay, so there we go. Now, what can we cancel out? We can cancel our K's because they have to be the same at the same temperature, and we can cancel our M value. So what does that leave us? It leaves us with these two parts right here, this one and this one. So it looks like we have 2 equal to 2, 0.4 divided by 0.2 is 2, and that quantity can be raised to the n. So it looks like n is equal to 1 again for this reaction. So we can say that this is first order with respect to B, or the rate order with respect to B is 1. Either way is acceptable. First order with respect to B. Actually, it's not B. Went into default mode with respect to the pressure of H2. So there's our first part of the reaction. So now we can do the next part of the calculation, and this time we're going to set reactions 2 and 3 equal. And if you look back at the table, you'll see that reaction 3 is bigger, that the rate of the reaction 3 is bigger. And now that you've got this, I'm going to erase this part so I can have a little more room to write. And we're going to do rate 3 over rate 2. Make sure you're writing it with parentheses and not with brackets. Make sure you're using NO and H2 and not A and B like I almost did earlier. It's very easy to go into default mode. So these are supposed to be 2's. So be careful when you do this because they'll throw different ones at us, different substances at us when we least expect it. Okay, so rate 3 is 0.01 atmospheres per minute. Rate 2 is 0.005 atmospheres per minute. We've got K3 over K2. The pressure of NO for rate 3 is 0.15. Should be atmospheres per minute. I have to admit that when I start doing them on my papers, on my keys, sometimes I will neglect to put the units. And here I'm running out of room, so I'm trying to write as small as possible. Rate 3 is going to be, or excuse me, the pressure of H2 for reaction 3 is 0.2 atmospheres. Now remember, now we can raise that to a 1. For K, for the second reaction, this is 0.075 atmospheres, and it's not atmospheres per minute, guys. I'm sorry. I'm sure you're sitting there wondering how I'm getting these units. These are just atmospheres, and I did the exact same thing. I just see it on the top. I'm not going to stop this video and do it again, though. I am simply going to correct it. This should be atmospheres. This should also be atmospheres. All of these are atmospheres. See, I would have had less chance of running out of room if I had seen that. And then for reaction 2, it is 0.4 atmospheres. And again, we can raise those to the first power. So correct those units real quick. My fault for getting those incorrect, but you can fix them. Now, what will cancel? K's. K's will cancel, and that's pretty much it. So what do we get for the rest of it? This is 2, taking 0.01 divided by 0.005. The next section, 0.15 divided by 0.075 is also 2, and it's going to be quantity raised to the m. And 0.2 divided by 0.4 is 0.5. It's 1/2, or 0.5. So in order to solve for this, I'm going to need to multiply both sides by 0.5. When I do, I get that 2 to the m is equal to 4. Well, if that's true, evidently m is 2 because 2 squared is 4. So that tells us that this reaction is second order with respect to the concentration of, or excuse me, to the pressure of NO. So what does that tell us about the rate law now? We can write the rate law as rate, and this is not in the correct place, it should be up there, but I'm just going to write it here. Rate is equal to K, pressure of NO, times the pressure of H2, and pressure of NO should be squared, pressure of H2 raised to the first, and we would get the rate law now by calculation, the same rate law that we would get by inspection. And that's how you can do this by calculation.